Look at a map of the ocean floor and something will immediately feel wrong. Most of it looks the way you'd expect. Mountains, flat plains, deep trenches running like scars across the bottom of the world. But in the middle of the Atlantic, there is something that doesn't fit. A hole. Not a trench, not a crack, a hole. And it leads somewhere your brain is not built to understand. You think you know what the ocean floor looks like. You've seen the diagrams. Dark water, rocky ground, deep trenches, hydrothermal vents. But the ocean floor has a feature so extreme, so genuinely strange, that scientists who study it still argue about what it means. There are places where the ocean floor simply opens up. Not in the way a crack opens. Not in the way an earthquake splits ground. In the way that the earth beneath you just stops existing. And what's below it is something that should not be accessible from the surface of this planet. So, what exactly is down there? And why did it take us until the 1970s to even find it? For most of human history, the ocean floor was a complete mystery. You couldn't get there. Nobody could. The pressure at the deepest parts of the ocean is roughly 1,000 times what you feel standing outside right now. At those depths, a submarine without the right hull would fold in on itself the way you'd crumple a paper cup. So for centuries, humans mapped coastlines, sailed across oceans, built entire civilizations around the sea, and had absolutely no idea what was underneath it. The first serious attempt to map the ocean floor happened in 1872, when a British ship called H.M.S. Challenger left Portsmouth and spent 3.5 years dragging instruments through the world's oceans. The crew measured depth by lowering weighted ropes over the side of the ship and waiting to feel them hit bottom. Some of those ropes were over 4 miles long. It took hours just to make a single measurement. By the end of the voyage, they had taken 492 depth soundings and discovered, among other things, that the deepest point on Earth was somewhere in the Western Pacific. They called it the Challenger Deep, but the technology to actually see the ocean floor, to image it, map it, understand its shape, didn't exist yet. That came later. And when it did, what scientists found was not what anyone expected. In the 1950s, 2 oceanographers named Marie Tharp and Bruce Heezen at Columbia University began stitching together the first real map of the Atlantic Ocean floor using sonar data collected by ships. Tharp was doing the drafting work by hand, plotting thousands of individual depth measurements onto paper, and she noticed something. Running down the center of the Atlantic, from near Iceland all the way to the tip of South America, there was a mountain range, not a small one. The largest mountain range on Earth. It stretched 40,000 miles when you included its full length wrapping around the planet. Tharp and Heezen called it the Mid-Ocean Ridge. But the ridge wasn't the strangest part. Running directly down the center of that ridge was a valley. A rift valley. A crack in the planet so deep and long that it made the Grand Canyon look like a sidewalk seam. Your body has a spine. The Earth has one too, and it runs along the bottom of every ocean on the planet. And this spine is not solid. It is splitting apart. Here's what's fascinating. The mid-ocean ridge is not just a geographic feature. It is an active wound. The tectonic plates that make up the ocean floor are spreading apart from each other, pulled by the slow churn of material deep inside the Earth. As they pull apart, hot liquid rock from the mantle, the layer beneath the crust, rises up through the gap and solidifies. Then the plates pull apart a little more. More rock rises, more solidifies. The ocean floor is essentially a conveyor belt being built in real time. In the Atlantic, the spreading rate is roughly 2 to 5 centimeters per year. That's about the same speed your fingernails grow. Slow enough that no human being has ever witnessed it directly with their eyes. Fast enough that over millions of years it reshaped entire continents. North America and Europe are moving apart from each other right now, while you're reading this, at a speed your fingernails would recognize. And here's where it gets stranger. If the ocean floor is constantly being built at the ridges, it has to be destroyed somewhere else. Otherwise, the Earth would keep getting bigger, and it doesn't. The destruction happens at subduction zones. These are places where one tectonic plate slides beneath another, diving down into the mantle where it melts back into the molten rock it came from. The Pacific Plate, for example, is slowly being swallowed beneath Japan, the Philippines, and the west coast of South America. The trenches at subduction zones are the deepest places on Earth. The Mariana Trench, the deepest of them all, is nearly 7 miles from surface to floor. If you dropped Mount Everest into it, the peak would still be a mile underwater. The pressure at the bottom of the Mariana Trench is 1,086 times what you feel at sea level. A styrofoam cup sent down on a research submersible comes back the size of a bottle cap. The water itself compresses under that pressure, becoming slightly denser than the water above it. For most of the 20th century, humanity had better maps of the moon than of the ocean floor. We sent 12 people to the surface of the moon before anyone descended to the deepest point of our own ocean. So the ocean floor has a life cycle, born at the ridges, spread across the ocean basin over tens of millions of years, destroyed at the trenches. And the hole, the real hole, is where this cycle exposes something it was never supposed to. In 2016, a team of scientists on the research vessel Atlantis published findings about a stretch of the mid-Atlantic ridge near the equator called the Romanche Fracture Zone. The Romanche Fracture Zone is a transform fault, a place where two plates are sliding sideways past each other rather than spreading apart. And in this zone, something unusual happens. The spreading at the ridge and the sliding of the fault create a gap where the crust doesn't just crack, it peels back. What's exposed beneath isn't more rock of the kind you'd normally find at the ocean floor. What's exposed is the mantle itself, the actual interior of the Earth, normally buried beneath miles of crust, sitting on the ocean floor where any instrument, or theoretically any creature, could reach out and touch it. Scientists call this a tectonic window. The crust opens like an eyelid, and the planet stares back. And here's the part nobody talks about. The mantle is not what you think. You probably imagine it as liquid. Red-orange molten rock, like what you see in a volcano. But the mantle is not liquid. Not exactly. It behaves like a solid if you push it quickly, and like a very slow-moving fluid if you push it over thousands of years. It's closer to hot glass than to lava, and when it rises to the surface at places like the Romanche Fracture Zone, it cools and hardens into a type of rock called peridotite. Peridotite is greenish-gray, heavy, dense, studded with crystals of the mineral olivine. It is the most common rock in the Earth's interior and one of the rarest on its surface, because almost none of it ever makes it through the crust intact. But at the Romanche Fracture Zone and at a handful of other tectonic windows around the world, it sits directly on the sea floor. Scientists can scrape it up, bring it to the surface, hold a piece of the Earth's mantle in their hands. Your skin has never touched a material that old. Peridotite from these sites has been dated to over 100 million years. Most of the rock on Earth's surface is younger than the dinosaurs. This rock remembers a world that existed before them, but the stranger story involves what that mantle rock does when it meets seawater. When peridotite comes into contact with water, it undergoes a chemical reaction called serpentinization. The rock absorbs the water, it transforms. The olivine crystals break down. New minerals grow in their place, primarily a group called serpentine minerals, which are soft, green, and fibrous. And as the rock changes, it releases heat, not from volcanic activity, from chemistry alone. The reaction is exothermic. It generates warmth from nothing but water touching stone. Scientists have measured temperatures of up to 90 degrees Celsius at sites where serpentinization is actively happening on the ocean floor. Not from a vent, not from magma nearby, from rock and water meeting for the first time. Your body uses chemistry to generate heat too. Every time you eat and your cells break down glucose, you produce warmth the same way, through a chemical reaction, not a fire. The ocean floor is doing, at a geological scale, what your body does at a cellular one. And here is where it gets complicated. Serpentinization also produces hydrogen gas. Hydrogen is one of the most energetically useful molecules on Earth. It's the fuel that stars burn. And when hydrogen seeps up through these tectonic windows, microbes eat it. Not just eat it, thrive on it. In 2000, scientists discovered a hydrothermal vent field on the mid-Atlantic ridge called the Lost City. It's unlike anything else found before it. Most hydrothermal vents, the black smokers discovered in 1977, are powered by magma. They reach temperatures of over 400 degrees Celsius and spew dark clouds of mineral-rich water. The Lost City is different. It's powered not by magma, but by serpentinization, the reaction of mantle rock and seawater. The vents at the Lost City are white, not black. They form towers of carbonate minerals, some of them 60 meters tall. The water coming out is hot, but nothing like a black smoker. The Lost City was found by accident, by a team that wasn't even looking for it. They were mapping the ocean floor nearby when their instruments picked up an anomaly. A field of tall white towers rising from the sea floor like a drowned cathedral, and the life living inside these towers is unlike anything else on the planet. Microbes that eat hydrogen and methane, that live in water with a pH close to 11, the same as household bleach, that thrive in an environment with almost no sunlight, almost no oxygen, and no connection to anything you would recognize as the base of a food chain. Here is the thing about these microbes. They may represent one of the oldest lineages of life on Earth. The theory of a serpentinization-powered origin for life on Earth has been gaining traction since the early 2000s. Before there was photosynthesis, before there was sunlight hitting the ocean surface, before there were any of the chemical reactions we associate with life as we know it, there may have been tectonic windows, mantle rock meeting water, hydrogen seeping up, microbes learning, over billions of years, how to eat it. If that's true, life didn't start on the surface of the ocean. It started in a hole in the floor. And here's what's strange. The same chemistry may be happening right now, on another world. Enceladus is one of Saturn's moons. It's small, covered in ice, orbiting a gas giant 900 million miles from the sun. In 2005, the Cassini spacecraft detected water vapor plumes erupting from Enceladus's south pole, plumes of liquid water escaping from beneath the ice and spraying into space. In 2017, analysis of those plumes found hydrogen gas, molecular hydrogen, the exact signature you'd expect from serpentinization. Scientists at NASA ran the numbers. The hydrogen levels were high enough to sustain microbial life indefinitely, if microbes were there to eat it. We don't know if they are, but the chemistry says they could be. Hydrogen gas, the same signature produced by serpentinization. The same reaction happening at the Lost City, on the mid-Atlantic ridge, at the tectonic windows of Earth's ocean floor. Maybe happening right now, beneath the ice of a moon orbiting Saturn. Which means if life started in Earth's tectonic windows, it may have already started there too. And if life started in Enceladus's ocean, it would be life that has never seen the sun. Life that has never needed it. Life that grew up in a hole in the floor of a frozen world, eating chemistry instead of light. You grew up doing the same thing, not eating hydrogen, but building your body from chemistry you didn't choose. Look at that map again. The hole in the ocean floor, the crust peeling back to show what's underneath. Scientists used to think the inside of the Earth was inaccessible, sealed away, unreachable, but the Earth keeps showing it to us, in tectonic windows, in vent fields, in plumes shooting off frozen moons 900 million miles away. The inside of the planet is not locked up. It leaks, and every time it does, life figures out how to eat whatever comes through. You are built from that same instinct, not the instinct for sunlight, for warmth, for food you can see and smell and recognize, the deeper one, the one that looks at a dark hole in the floor of the world and decides to climb in anyway. That is not a metaphor. That is the most ancient thing about you.